Hi everyone, welcome to AI Crack channel. This is Akash Jungwar and today we'll be studying Continuity Lecture 2 and we'll be talking about discontinuities in detail, basically types and reasons of discontinuities. So let's begin a lecture with reasons of discontinuity and the first reason is limit doesn't exist. Okay, it has two further subdivisions. The first one is LHL is not equals to RHL. Basically limits are existing but they are not same, they're not equal. And the second case is limits don't exist. Okay, so basically we can say that they're not defined or they're infinity. Okay, in either of the cases we can simply say that limit doesn't exist. Okay, now let's see how these can be represented in graphs. So the first case is, let's say we are plotting a graph of this sort and we have an open circle over here and this graph over here. Okay, now in this case LHL is not equals to RHL for x equals to 0. At x equals to 0, LHL equals to, let's say this point is 2, so LHL equals to 2 and let's say this point is 1, let's say. Okay, so RHL equals to 1 over here. Okay, so LHL is not equals to RHL, that's why limit doesn't exist and function is discontinuous. The other case would be, let's say function is defined like this one. So in this case LHL goes towards infinity and RHL goes towards negative infinity, right? In both the cases limit doesn't exist, limit does not exist. Okay, so that's why we can say that function is discontinuous. Okay, now let's talk about second reason, limit exists but function is not defined. Let's look at this one. Over here we can take this example. We have a modulus kind of function but we have an open circle at x equals to 0. So over here LHL equals to RHL equals to 0. We can simply see that, right? Over here the values are approaching 0 from both left and right hand side, right? So limit, left hand limit and right hand limit both are 0, but at x equals to 0 we have an open circle. Basically function is not defined. So in this case we can say limit exists but function is not defined. That's why overall function is discontinuous. Okay, now third case is limit exists, function is also defined but they are not equal. So we can take again a similar case. Let's say we have again a modulus type of function, open circle over here but the function is defined over here. Okay, let's say this value equals to 5. Now LHL equals to RHL equals to 0 for x equals to 0. If you're talking about x equals to 0, both limits are 0 but function value is 5 over here. Function is defined but defined somewhere else. So in that case this is not equals to f of 0. So that's why function is discontinuous. Okay, so these are the three conditions, these are the three reasons of discontinuities. Now here are certain important points to remember. Every polynomial function and rational function is continuous except for the points where denominator becomes 0. As we have studied in the functions lecture that all polynomial functions, linear, quadratic, cubic, biquadratic and even functions of higher degree, they all are continuous functions, right? And we know that rational functions are created with the help of polynomial functions only. Basically if you divide two polynomial functions we are going to get a rational functions. Let's say we have two polynomial functions, the first one is fx, second one is gx. Now we have created one hx rational function, that is fx by gx. Now when gx equals to 0, function won't be defined, so at those points this entire rational function would be discontinuous because gx equals to 0 and function is not defined at those points. Okay, at all other points polynomial functions are continuous for all points, and for rational function we have to look at the points where denominator becomes 0. If you exclude those points they are continuous everywhere. Okay, now the second point is exponential functions, log functions, trigonometric functions, inverse trigonometric functions, modulus functions are continuous in their domain. We have discussed that a major chunk of functions are actually continuous in the domains. I'm not saying all of the functions, but these kind of functions are always continuous in their domain. You can just check it and you'll find that these functions are always continuous in their domain. It's better to remember these functions. Okay, now third point is most important, always check for discontinuity in case you see GIF functions and fractional part functions. So whenever you see an integral point in case of GIF functions and fractional part functions, you have to check for the discontinuity. For example, let's take, we have x, GIF of x. In this case we'll be checking at 1 2 3 4 and so on, basically all the integral points. Let's say we have x square. In that case, we'll be checking at 1, root 2, root 3, 2, and so on, right? Because for root 2, this function would become integer, right? For root 3 also, this function would become integer. So at all points, when this value is taking integral values, in those cases, we have to check the discontinuity of the function, okay? So we have to be very careful whenever we are dealing with GIF function and fractional part functions in case of continuity and discontinuity. Okay. So remember all these 3 points for easy solving of problems. Now let's solve this example. Find the points of discontinuity of the following functions. So the first function is fx equals to 1 upon x square minus 3 mod x plus 2. Now this is a modified version of rational function. This is not exactly a rational function because we cannot call this as a polynomial function, but it's a modified version of rational function. This is polynomial in the numerator, and this is also a modified version of polynomial function with a modulus sign. Okay, so that's why you cannot directly call it as a rational function. Now, main concept is same. When denominator is becoming 0, this entire function won't be defined. That's why we have to find those points where this function is becoming 0, and those are the points of actually this function being discontinuous. Okay, so x square minus 3 mod x plus 2 equals to 0. We have to find out these points. Okay, now we can open up this modulus in two ways. X square minus 3 x plus 2 equals to 0, or x square plus 3x plus 2 equals to 0 with a plus sign or negative sign, right? So for this case, we'll be getting x minus 2, x minus 1 equals to 0. For this one, we'll be getting x plus 1, x plus 2 equals to 0. Okay, so for here, we'll be getting x equals to 1, x equals to 2, and for here, we'll be getting x equals to minus 1, x equals to minus 2. Now, important thing is, when we're opening this bracket as positive, we're assuming that x is greater than equals to 0. For this case, we're assuming that x is less than 0 because over here, we are opening up modulus with positive sign. Over here, we are opening up modulus with negative sign. So we have to assume these conditions before opening up these brackets. And now what we've got values over here, 1 and 2 satisfy this condition, and minus 1 and minus 2 satisfy this condition. So that's why we have 4 points over here for this function to be discontinuous, right? 1, 2, minus 1, minus 2. Okay. Now let's look at the second function. We have 1 upon 1 minus e raised power x minus 1 divided by x minus 2. Now numerator is constant, which is continuous. In denominator, we have to find out all the values where this function is becoming 0, right? Where function is not defined. Also, the other condition would be there can be certain points where this function is not defined, and the definition of this entire function is dependent on this function also. So we have to check all the points where this function is also not defined, and all the points where this denominator is becoming 0. Okay, so first condition is 1 minus e raised power x minus 1 divided by x minus 2 equals to 0. Now for that, this has to be 0. This becomes 0 1 when x equals to 1. So when x equals to 1, this becomes 1 and this entire becomes 0. Okay, so x equals to 1 is 1 point. Now for this function to be not defined, x minus 1 divided by x minus 2, for this case x minus 2 equals to 0, right? Because this is again a rational function. This is actually a rational function, and for rational function to be not defined, denominator should be 0. Okay, so x equals to 2. We have 2 points, x equals to 1 and x equals to 2, and for both of these points this function is not defined, and when this function is not defined, actually it becomes discontinuous. Okay, why are we not considering other points? Because at all points exponential function is continuous, polynomial function is continuous, right? Over here as well, all the other points, this is actually a polynomial function is continuous everywhere. So we have to find only those points where the function is not defined, right? And function is not defined when denominator becomes 0 or the function itself is not defined. Okay, and now let's talk about different types of discontinuities, and we have two broader types: removable and non-removable. So in case of removable, we say that limits exist. In case of non-removable, we say that limits don't exist. Okay, now that is the basic differentiation between these two types of limits. Okay, now for removable, we have two further subdivisions: missing point and isolated point. In case of non-removable, we have three subdivisions: finite, infinite, and oscillatory. Let's look at each of them individually in detail. Okay, so the first one is missing point. Let's define this function as Let's say a modulus kind of function with an open circle at x equals to 0. In this case, the point is missing. Function is not defined at x equals to 0. It's defined everywhere, but at one single point, function is not defined. We can see that LHL equals to RHL equals to 0. At x equals to 0, left hand limit and right hand limit both are equals to 0. But function is not defined at x equals to 0. The point is missing over here. So that's why function becomes discontinuous, and this type of discontinuity is called as missing point discontinuity. Okay. Now the second one is isolated point. Now let's take the same example with a slight variation. Okay, so we have this modulus kind of function. We know that LHL equals to RHL equals to 0, but that is not equals to f of 0 because f of 0 is defined over here. In case of missing point, function was not at all defined over there. In case of isolated point, function is defined, but the point is isolated somewhere else rather than over here. Okay, so this is the example of isolated point. Limits are existing, but they are not equals to the function defined over here. Okay, function is defined somewhere else. Now, if we talk about the non-removable type of discontinuity, the first one was finite. Okay. Now, in this case, let's take this example, very standard one. So we have this one and this one, open circle over here. And this case, limits are not existing, but they are finite. Okay. Let's say this value is 2, this value is 1. So LHL equals to 2, RHL equals to 1, and they are not equal. Okay. So in this case, we can simply say that limit doesn't exist because they're not equal and they are finite also. Okay. So this is the finite kind of non-removable discontinuity. Now second one would be infinite. As the name suggests, we can simply say that the function would look like something of this sort. LHL equals to infinite, or you can say not defined. RHL equals to infinite, or you can say not defined, right? So in both the cases, limits are infinity, and that's why they are infinite type of non-removable discontinuity, and limit doesn't exist over here. Okay. And now the third one is oscillatory. The example is sine of 1 by x, and it's very interesting. Let's say x is approaching 0 and we take two values x1, x2. x1 is 10 to the power minus 5, x2 is 10 to the power minus 6. Both are approaching 0, right? They are very insignificant, very small values, okay? But their implication on 1 by x would be huge. If we take x1 over here, we'll be getting sine of 10 to the power 5. For x2, we'll be getting sine of 10 to the power 6, right? So difference in arguments is huge. This is 10 to the power 5, this is 10 to the power 6. Argument difference is huge over here. And now if you plot this graph where x is approaching 0, in that case, any small change, very small change in x would create huge implications, huge differences in arguments, right? Let's say we have multiple values of x very close to 0, and for all those x values, we have different kinds of argument and different values of sign, right? For different kinds of x values, which are very close to 0, we have different kind of sign values because of their huge implications. So every small change would create a different kind of value for this function. Agreed, right? So this would create this kind of function over here, and eventually it would die off to 0, because when x is approaching infinity, this argument would become 0 and sign would become 0 ultimately. But when it's close to 0, this function would oscillate, because any small change in x which is close to 0 would create huge differences in arguments. That's why the function value would oscillate near 0, and as we approach towards infinity, it would become 0. Same happens over here as well. Okay. So this is the oscillatory kind of limit, where limit value is not fixated at one single point. It's oscillating near 0. Okay. And now let's solve this last example. We have fx equals to e raised power 1 by x minus 1 divided by e raised power 1 by x plus 1, where x is not equals to 0 and 0 when x equals to 0. So it's a piecewise function, and we have to find out which type of discontinuity it has. Okay. So first of all, we have to see if the limit is existing or not. So for this one, e raised power 1 by x minus 1 and e raised power 1 by x plus 1, we have to find out LHL and RHL. Okay, let's find out LHL. For LHL, what we'll be doing? We'll be doing f of 0 plus h. Okay, so that would give us e raised power 1 upon h minus 1 divided by e raised power 1 upon h plus 1. Now, if we take out e raised power 1 by h as common, this would give us 1 minus 1 upon e raised power 1 by h divided by 1 plus, again we have taken out 1 by e raised power 1 by h is common, multiplied by 1 plus 1 upon e raised power 1 by h. Now we know that e raised power 1 by h would go to infinity because h is very small positive number, right? H is very small positive number, and 1 upon very small positive number would lead to positive infinity. So that would mean e raised power 1 by h is going to positive infinity. So this term becomes insignificant. This term becomes insignificant. This gets cancelled out. What we are getting, limit as 1. So RHL equals to 1. Now if we talk about LHL, for that we'll be doing f of 0 minus h. That would give us this function. Now this is going to negative infinity because h is positive number, so minus h is negative, and 1 upon very small negative number, that would lead to minus infinity. E raised power minus infinity would lead to 0. Similarly, this would be 0, right? Close to 0. So this would become minus 1. This becomes insignificant. This becomes insignificant. So answer would be minus 1 upon plus 1. So left hand limit comes out to be minus 1. RHL was coming out to be 1, and left hand limit was coming out to be minus 1. So in this case, limit does not exist. When limit does not exist, it's non-removable. Okay. And what type of non-removable? Finite type, because limits are finite. Okay. Very simple example. So today's lecture was still here only, and in the next lecture, we'll be talking about remaining topics of continuity. So let's meet in the next lecture. Thanks for watching.